Okay, so this is a series which I am bringing for discussion about AP Physics 1, where we'll go through all the questions and discuss how you can attempt each one of them. Okay, we'll get started with the very first question from 2025. Okay, let's read. So a student has a cart of mass mc and a block of mass 1 upon 5 mc. So this is 1 upon 5 and this is what we have as mc. At time t is equals to 0, the cart is moving to the right across a horizontal surface with constant speed vc. Okay, so let's just write over here that this particular cart is moving in this direction with a velocity vc. Okay, now and the student releases the block from the rest, and this is just being released from the rest. Now at time t is equals to t1, what is observed is the block collides with and sticks to the top of the cart. So it just sticks over here. The block does not slide on the cart, it is just going to be sticked over there. And at time t is equals to t2, the block cart system continues to move to the right with a constant speed vf. So let's say here the constant speed is going to be vf. Okay, let's move to the first question on this. What does it say? On the axis shown in the figure 2, sketch a graph of the magnitude px of the x component of the momentum of the block cart system as a function of time from t is equals to 0 until t is greater than t2. Okay, so initially what I can say is, if I consider this particular system, for this particular system there is no external force. Okay, so I can say that net external force is 0. So whenever the net external force is 0, we can say that the momentum is going to be conserved. So initial momentum is going to be same as final momentum. Now when there is a block colliding with this particular cart, again if you observe there is no external force involved in it. So I can say that in the final situation or in the middle situation, whatever we have, in all the cases the net external force we have is 0. Here also we can say that net external force is 0. Here also net external force is 0. So whenever net external force is 0, what we can say is the momentum is going to be conserved. As the momentum is going to be conserved, so whatever, let's say here at this particular point of time the momentum was p naught, so here also I can say that the momentum is going to be p naught, and here also I can say that the momentum is going to be p naught. So for all the time period starting from t is equals to 0 till t is equals to t2, the momentum is going to be constant. Okay, so what I can say is I can just say here, okay, this is some value p naught, and I can draw a straight line from here till here. So this is going to be a straight line. So p naught is going to be constant. Okay, perfect. Now let's move to the next one. Derive an expression for the speed vf of the block cart system after time t is equals to t2. So here we need to figure out what is the value of this v final. We need to figure out what is the value of v final in terms of this mc, vc and physical constants whatever are required. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so as we just discussed, what I can say is, as the net external force is 0, momentum is going to be conserved. So I can say that initial momentum will be equals to final momentum. Pi is equals to pf. Okay, now if I go back over here, what is the initial momentum? I can see that in the initial case only and only this particular cart is moving. Okay, so if I want to write p initial, I can say that only this cart is moving and it is moving with a velocity vc. So I can say that initial momentum is going to be mc times the velocity which is vc, and at the final condition over here the total mass is this. The total mass is now the mass of the cart plus the mass of the block. So P final is going to be mass of the block plus mass of the cart times V final. Okay, and we have been given the masses. So mc is the mass for the cart and 1 upon 5 mc is the mass of the block. So let's put these equations over here. So what I can get is, for initial I will get as mc times vc is equals to, the total mass is going to be mc plus 1 upon 5 mc times, it should be v final. Okay, So let's just do fraction addition. So mc times vc will be 5 plus 1, which is going to be 6 upon 5 mc times v final. Okay, now both the sides I have mc, I can simply cancel it out, and from here I can say that 5 upon 6 vc is equals to v final. So this is the expression for 5 upon 6 vc is equals to v final. Okay, perfect. Let's move on to the next question. What does it say? Derive an expression for the change in kinetic energy delta K in the block cart system from t is equals to 0 to t is equals to t2 in terms of, again, same whatever constants we have, mc, vc and all the physical constants. And again, begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so what is change in kinetic energy? Change in kinetic energy is nothing but whatever was the final kinetic energy minus whatever is the initial kinetic energy. So I can say that initially I had a mass mc moving with a velocity vc, and finally the total mass I have is mc, and this is 1 upon 5 mc moving with a velocity which is v final. Okay, now let's find out what is k initial, let's find out what is k final. So if I want to find out k initial, what is going to be k initial? It's simply half times what is the mass, we have mc, times what is the velocity, it's vc square. So half mc times vc square. Now if I want to find out k final is going to be half times what is the total mass. Total mass mc plus 1 upon 5 mc will be 6 upon 5 mc times v final square. Okay, and what was v final? V final was nothing but 5 upon 6 vc. So I can say that this is 5 upon 6 vc whole square. Okay, so I'll just open the bracket, so I'll get 1 upon 2 times 6 upon 5. So 6 upon 5 and 5 upon 6 will be cancelled out, and we will have is only 5 upon 6 over there. So 1 upon 2 times we'll have 5 upon 6 times mc times vc square. Okay, and if I just this will become 5 upon 12 mc times vc square. Okay, now once we have all of this, we can now put it in the first equation, k final minus k initial. So delta k is equals to k final minus k initial. So what is k final? I have k final as 5 upon 12. So this is going to be 5 upon 12 mc vc square minus, it's going to be 1 upon 2 mc vc square. Okay, so the LCM is going to be 6. I'll have 5 minus 6, so 5 minus 6 upon 12 mc vc square. So finally I will get my answer as minus 1 upon 2 mc vc square. Okay, this is going to be my final change in kinetic energy. Okay, perfect. Now we are at the last part of the first question. What does it say? Consider the case where a new block is dropped and collides with the top of the cart. Again, a new block is dropped and collides with the top of the cart. The new block now slides along the cart during the collision but does not slide off the cart. Okay, so for example, if this is the mass mc, so this particular block is falling down on this, it's falling down on this, but if it is falling down on this, it is just sliding it, but it is not going to fall down. Okay, so from here, what does it say? The time interval from when the new block collides with the cart and moves together with the cart is delta t. During delta t, there is a frictional force. There is a frictional force between the new block and the cart. We need to figure out, indicate whether the x component of the momentum of the new block cart system increases, decreases, or remains constant during the delta t. Now again, momentum is based on what? Momentum is only based on if the net external force is 0, then momentum is going to be constant. so momentum is constant. But if the net external force is not zero, the momentum is not going to be constant. So let's just analyze over here. So I have a mass of this over here moving in this direction, and I have another mass on top of it. Let's say this is another block. So if this block is applying friction on MC, so this block will try to put a friction force in this direction for this let's say F block due to M, and this particular will try to put a friction force in this direction. Hence the net friction force will again be zero because of Newton's third law. And again, this is all a part of internal forces. These are all internal forces. So out of the system, I can say that the net external force is still zero. F external is still zero. So as F external is still zero, I can say that initial momentum is going to be final momentum. Hence, it is going to be conserved. So it should now remain constant. Okay. Welcome to this series on AP Physics previous year questions. So this is the question number 2 of year 2025. Okay, let's move to the question now. So a block of mass M is released from rest at position x is equals to 0. So somewhere over here we are releasing it from rest. So the initial velocity is going to be 0 near the top of a ramp. The ramp makes an angle of theta with the horizontal. So this is the angle theta over here. The block slides down the ramp with negligible friction. So we can consider that the net friction is 0. At x is equals to 8t, the block makes the contact with an uncompressed spring with the spring constant as k. So given is the spring constant is k, and at 8d is where the block and the spring are going to be collided. Okay, the spring is then compressed and the block momentarily comes to rest at x is equals to 12t. So the 12t is the distance at which I can say from where the direction is going to change. Okay, now figure 1 shows the instance when the block is at x is equals to 0. So this is at x is equals to 0, this is at x is equals to 60, and this is at x is equals to 10d. So we have given three different scenarios for the cart. Okay, now let's move further. What does the question say? Figure 4 shows an energy bar chart that represents the kinetic energy of the block, the gravitational potential energy UG, and the spring potential energy US. So this is the bar we have. So we have a kinetic energy, we have a gravitational energy, and we have the spring potential energy. Okay, so using this we have a diagram 4 where it shows what are the values of each kinetic energy, gravitational potential energy, and spring potential energy. Okay, now at the instant that the block is at 10d, so this is given at the instant when x is equals to 10d. So this is the scenario when x is equals to 10d, that k is given as 7 E naught, the gravitational potential energy is given as 2 E naught, and spring potential energy is given as 3 E naught. So I can say that total energy over here is kinetic energy plus gravitational potential energy plus spring potential energy. So I can say 7 E naught plus 2 E naught plus 3 E naught, 7, 8, 9 plus 3 is going to be 12 E naught. So total energy of the system we have is 12 E naught. Okay, very good. Now the gravitational potential energy UG of the block spring earth system is defined to be 0 when the block momentarily comes to rest at x is equals to 12d. So this is where we consider this particular line as a reference line where the potential energy is considered as 0. Okay, now draw shaded bars that represents the values of kinetic energy UG and US to complete the energy bar charts in the figure 2 and 3. So we need to compile for x what will be the charts for x is equals to 0 and what will be the charts for x is equals to 6d. Shaded bars should start at the dashed line that represents 0 energy, represent any energy that is equal to 0 with a distinct line, and okay. So first thing what we understand from here is that the total energy of the system is 12 E naught. Okay, total energy of the system is given as 12 E naught. Now if I go back to x is equals to 0, can I say, as we are released from rest, it says that it is released from rest, so can I say kinetic energy in this case is simply going to be 0? Okay, kinetic energy is going to be 0. Now the spring is also uncompressed, so I can say that spring potential energy is also going to be 0. And we know that what is the total energy? Total energy of the system, we know that total energy is given as 12 V naught. So if I want to say, can I say total energy will only be comprised of gravitational potential energy, hence the value of Ug is going to be 12 E naught. Okay, kinetic energy will be 0 as velocity is 0. Spring potential energy will 0 as it is uncompressed, so this is uncompressed, and hence total energy will be equals to Ug. So total energy will be simply equals to the gravitational potential energy over here. So on figure number 2, I can say that kinetic energy is 0, the spring potential energy is also 0, and this particular potential energy, gravitational potential energy, is going to be Ug. So something over here like this. Okay, so x equals to 0 was a little easier. Now let's see what is the next part. Next part is we need to find out for x is equals to 6d. Okay, we need to find out for this. Let's go back over here. So if I consider this thing, let me just draw a diagram. Let's say this is what we have. This is 12d, this is theta. So if I know what is this height, I can write down the value of gravitational potential energy at this. So I can write it down for this. So I know that at this point Ug is equals to 12 V naught. So I can write down h in terms of d and theta. So can I say sine theta over here? Sine theta is nothing but sine theta is equals to, I will just insert a new page. Okay, so sine theta is equals to what? We have h upon 12d. So I can say that the value of the height h is nothing but 12d sine theta. Okay, so the value of h is 12d sine theta. Hence I can say that gravitational potential energy at Ug is going to be nothing but m times the gravitational times height. So here height is what we have as mg 12d sine theta. So this is Ug, and this should be equals to what we have as 12 E naught. Okay, this should be equals to 12 E naught. That is what we already know. Hence now I can say that if I cancel out 12 with 12, I can say that the value of mgd sine theta is nothing but E naught. So for every value of d, I can say that the energy is going to be E naught. Okay, hence here I can say that it is at a distance of what? 6d. So I'll say that okay, this is at a distance of 6d, so total is 12. This is at a distance of 6d, so this should be 6d sine theta. Hence total energy is 12 V naught, so this should be half of it. So at x is equals to 6d, the potential energy is going to be mg 6d sine theta, and we know the value of mgd sine theta. What is the value of mgd sine theta? It's E naught. So I can say that I can simply now replace the value of mgd sine theta. Okay, so it's going to be 6 times E naught. So Ug is equals to 6 E naught. Okay, now let's go back. So here I can say that there is some kinetic energy. So kinetic energy is not zero. Kinetic energy is not zero over here. I know now what is the potential energy. Potential energy, I know that it is 6 E naught, and total energy is what I know. One more thing we know is the spring potential energy. So what is the spring potential energy? As it is not compressed, so it is again going to be 0. So total energy is 12. If Ug takes 6 E naught, so what is left? Again 6 E naught is left. So 6 E naught is what will be the kinetic energy. So kinetic energy will be nothing but total energy minus Ug. So 12 E naught minus 6 E naught. So that will also be 6 E naught. So now we have the value of kinetic energy equals to the value of gravitational potential energy, and the spring potential energy is going to be simply 0. So I can draw it something over here like this. So this is going to be for K, this is going to be for U, and this is going to be for spring. Okay, 6 E naught, this is also going to be 6 E naught, and this is going to be just 0. Okay, so this question had a lot of analysis. Let's go to the next question. Okay, figure 5 shows the block at x is equals to 0 when the block is released from rest. Okay, similar thing. And the block at x is equals to 12d when the block momentarily comes to rest, again against the compressed spring. Now starting with the conservation of energy, derive an equation for the spring constant K, express your answer in terms of m, theta and d and all the physical constants as appropriate. And we can start by always writing whatever is the principle we know. Okay, now I know that in this particular thing, let's write it down. I know that here the kinetic energy is 0, right? The potential energy we already know, it is 12 V naught, and we know that the spring energy is also 0. So kinetic is 0, potential is 12 V naught, and spring energy is also 0. At this point, as it says that momentarily comes to rest, again the kinetic energy becomes 0. Also, in the previous question we know that Ug is considered to be 0 at x is equals to 12d. So here again one more thing is 0, that is Ug. So I can say that gravitational potential energy is also 0. And last thing, that is spring potential energy. Spring potential energy, from where does it start? Let's go back to the equation. So it is from 8 over here. It is compressing from 8d to 12d. So I can say that delta x from here to here, the delta x is going to be 4d. Hence the spring potential energy is going to be half k times 4d whole square. Okay, so now once we have written all the energies, we can use the formula, right? Conservation of energy. So what does the conservation of energy say? Energy in the initial condition should be equals to energy in the final condition. Now I can write it. So K initial plus Ug initial plus U spring initial should be equals to K final plus Ug final plus U spring final. Now we already know a few things. So I can say K initial is 0, U SI initial is 0, K final is 0, Ug final is 0. So what I get last at is gravitational potential energy in the initial condition will be equals to spring potential energy in the final condition. Okay, now here we have already derived what is Ug. So Ug is given as mg d sine theta. So I can use that value over here. So Ug is equals to Us, this is in final and this is in initial. I know this is mg d sine theta, and U final I have already calculated over here, that is half k 4d square. So equals to half k 4 4s are, I can write it as 16d square. Okay, so I can now cancel out d and this square from here, and I can cancel out 2 1s are 2, 2 8s are 16. And what do we need to find out? We need to derive the next constant for k. So we need to find out the value of k. So I can say that the value of this is going to be mg sine theta divided by 8, and d will go down. So 8d is equals to the value of k. Mg sine theta over 8d is equals to k. Okay, sorry, I missed one thing. So here it's not mgd sine theta, it's 12 mgd sine theta. So if I put one more 12 over here, so here we discussed that it is Ug is equals to mg 12d sine theta, right? So I can say that 12 mg sine theta, so 4 3s are 12, 4 2s are 8. So final answer should be K is equals to 3 upon 2 mg sine theta over d. So this should be the final answer. Okay, perfect. Let's move to the next part. Okay, again there is a diagram. Figure 6 shows a graph of the energy of the system as a function of the position of the block from x is equals to 8d to x is equals to 12d. So this is an energy with respect to position graph starting from the distance x is equals to 8d and goes up to 12d. Okay, and this graph is for spring potential energy, that at 8d it was 0 and gradually at 12d it becomes maximum. Okay, now sketch and label a line or curve that represents the total mechanical energy for the block spring earth system as a function of the position of the block from x is equals to 8d to 12d. So basically we need to draw the curve or draw the line for total mechanical energy. We know that mechanical energy is always conserved. So if the mechanical energy is always conserved, I can say that it is always going to be constant. So it always going to be the value of 12 V naught. So I can say this is total energy. Okay, so this is the first part of the C. Now what does the next part say? Sketch and label a line or the curve that represents the gravitational potential energy. So gravitational potential energy, what was that? We had just written it in this way, that gravitational potential energy is equals to mgh, and it is dependent on the height, and height is dependent on whatever is the distance. So if the distance is 6d, the height becomes 6d sine theta. If the distance is 12d, it becomes 12d sine theta. So whatever is the height, it becomes the value times d sine theta. So I can say that at 8d it's going to be how much? 12 V naught minus 4 E naught. So at 8d I can say that, so this entire thing is 12d sine theta. So this is 8d and this is going to be 12d. I can say that at 8d the total energy is going to be 4 V naught. So this is going to be just 4 E naught. So at point this, the energy is going to be 4 E naught. Now what about 9d? So 9d, it is again going to be 12 E naught minus 9 E naught. So it's going to be 3 E naught. So at 9d it should be somewhere over here. At 10d it should be somewhere over here. 11d 1 and 12d it should be 0. So I can see that it's a linear line, something over here like this. Okay, so this is how the line goes. So this I can write it as, this is gravitational potential energy, and it is going to be a linear. Okay, and last question, last part of the second question, what does it say? Indicate whether the speed v velocity at a distance 9d is greater than, less than or equal to the speed v8d of the block at x is equals to 8d. So let's simply compare the equations at x is equals to 8d. So at x is equals to 8d, I know that spring potential energy is 0. We know that spring potential energy is 0. The gravitational potential energy is 4 E naught that we had just written. So it's going to be 4 E naught. And kinetic energy will be how much? It's going to be 12 minus 0 minus 4 E naught. So it's going to be 12 minus 4. That's going to be 8 E naught. So kinetic energy at this point is 8 E naught. Okay, now let's write it down for at x is equals to 9d. So at x is equals to 9d, I know that I know definitely about gravitational energy. So gravitational energy is going to be 3 E naught. But now I have to find out the gravitational potential energy from the graph. So I can see that this is 3 E naught, but this is little less than 1. So I can say that US is less than E naught. So if US is less than E naught, can I say when I do kinetic energy is equals to 12 E naught minus 3 E naught minus the potential energy. So this total thing is definitely going to be more. right? As I'm subtracting, as this amount is less, US is less than E naught, or I can also write it in terms of comparison. So what I can say over here is that UG plus US is definitely going to be less than 4 E naught. Okay, and now if I subtract from 12 on both the sides, so 12 minus UG plus US less than 12 minus 4 E naught, I'll get the value of kinetic energy, which is less than 8 E naught. Okay, so as the kinetic energy is less than 8 E naught, what I can say this, so as kinetic energy at 9D is less than 8 E naught, and kinetic energy at 8D is equals to E naught. So definitely the velocity of 8D is going to be greater than the velocity of 9D. So option number B. Okay, welcome to the series where we will be discussing about AP Physics 1 previous year problems. This video we will be discussing on question number 3 from the year 2025. Okay. So students are investigating balancing systems using the following setup. So here we can see that there is a meter stick which just shows what are the distances from this particular axis. Okay, I can see there is a spring scale which will be used to measure what amount of force we are putting over here. So let's say this just measures the force given. There are a few holes at 60, 70, 80 and 90 centimeters, and there is a block with a hook over here. Now we need to find out, the students do not have a direct way to measure the mass of the block. So the block cannot be attached to the spring scale. So either we cannot attach the block over here, and they do not have a direct way to find out the mass of block m0. Okay, let's look at the first part. What does it say? Describe an experimental procedure to collect the data that would allow the students to determine the value of m0. Okay, so for example, let's say if I am attaching this particular block of mass m0 at this particular hole somewhere over here like this. So because of this, I can say that at this particular 80 centimeters distance, I will have a force which is m0 g, and at this point I will have a force downwards which is ft. Now this force is constant, but we can change the variable force over here, and whatever is the amount of force we will be knowing from here, which is the spring scale. As this is the axis of rotation, I can say that the torque due to this force is going to be in the anti-clockwise direction, and the torque due to this is going to be in the clockwise direction. So when the net torque becomes zero, I can say that the torque because of the spring scale will be balanced by the torque of the block. So torque of the spring will be balanced by the torque of the block, and this is where I can say we will be able to find out the distance. So now how can I find out the torque of the spring? So from here I can say this is 50 centimeters of distance. So torque of spring will be how much? The force of given by the person multiplied by the 50 centimeters. And when I want to find out the torque of block, so whatever is the distance, I will be knowing what distance it is. Either it is 10 centimeters from the axis, or if it is 20 centimeter, 30 centimeter, 40 centimeter. So it is going to be m0 g multiplied by x centimeter, where x is known, x is a known value. So when we equate this, I can say that I know the value of x, I know the value of 50 centimeter, I also know the value of f, I know the value of g. I will be able to figure out the value of m0. Okay, so what we need to do is, here the question wants us to give us an experimental procedure. So what will be an experimental procedure? We start putting mass m0 over here and figure out what is the spring scale reading. Put the mass again at this, figure out what is the scale reading, put it at 80 centimeter, figure out again scale reading, and do it at 90 centimeter, and at last figure out what is the spring scale reading. So with this continuous experiment, we will be able to figure out what is the mass of m naught. So another way of writing this is going to be, what we need to do is attach the block of unknown mass m naught through one of the small holes in the meter stick. Okay, these are the steps. So measure the distance from the stand to the block. So we'll just figure out what either as the distance is 10 centimeter or the distance is 20 centimeter, depending on where the block is kept. And we need to record the force reading from the spring scale when the meter stick becomes horizontal. So when does it become horizontal? When the torque, the net torque becomes 0 and all the it becomes in an equilibrium position. Now what we'll do is we'll simply repeat the data collection by attaching the block to the meter stick through a different small hole in the meter stick. So 70, 80, 90 centimeters, we'll have to just repeat it. Repeat the measurements by attaching the block at each of the small hole locations numerous times. So we just need to keep on repeating the same process. Okay. Now moving to the next one, what does it say? How the data collected in part A could be graphed and how the graph would be analyzed to determine the value of m naught. Okay, so how can we graph it and how can we utilize the data? So we know that a graph of the force as a function of the distance from the stand to the block could be used to determine the unknown masses. So whatever we have just written in the previous case, whatever I wrote over here. So I know that the torque because of spring scale will be equals to the torque because of the block. So force reading we know multiplied by that is 50 centimeters, that is also we know, equals to the value of m naught times gravity is what we know times x centimeter is also what we know. Now so if I draw a graph of the force as a function of the distance, so if the force is a function of the distance, this particular slope of the graph times the distance from the stand to the spring scale divided by g will result in the value of unknown mass m naught. So I can say m naught is nothing but f times 50 divided by g times x. So this is how we'll get the value of mass m naught. The slope of the graph times the distance from the stand to the spring scale divided by the g will result in the value of the unknown mass m naught. Okay, perfect. Now next thing, the student have an identical meter stick of mass m that is now attached to an axle that is fixed to a wall. So this is a different scenario. The meter stick is free to rotate, either you can put it over here or here or here or here, anywhere we can put the meter stick, and it is simply going to change the angle. If it is over here, the theta will keep on increasing, theta increases. The meter stick is suspended horizontally by a string that is connected to a spring scale of a negligible mass. Okay, here what do we need to find out? The angle theta that the string makes with the meter stick can be varied by attaching the string to one of the pegs located along the wall. So we can simply move it from here to here. And based on that, we can also figure out what is the force reading over here. So this will tell you the force reading and angle we can already measure. So this is the table 1, which shows the experimental data 22, 21, 31, 17, 36 degree. The force required is 13 newtons, 45 degrees, 12 newtons, like that. Now the students correctly determine the relation between ft and theta. So this is already determined, ft and theta, and they create a graph with 1 upon sine theta plotted on the horizontal axis. So I can say that the graph will have ft is equals to 5 mg upon 6 times 1 upon sine theta. So this thing is already on the x-axis. Now let's read the question. What does it say? Indicate what measured or calculated quantity could be plotted on the vertical axis. So definitely on the vertical axis, which quantity should be there? Ft, whatever is the force. I can say vertical axis, it should be Ft. Now on the blank grid provided, create a graph of the quantities indicated in part C1 that can be used to determine the value of m. Use table 2 to record the data points or calculated quantities. So basically we need to draw the graph of this. Okay, so I'll just get the graph how it looks once you plot the values. So graph is not about this. So in the graph we need to plot a graph between 1 upon sine theta and f trans f whatever is the given. So we already know the values of theta, we know what is ft, so we'll have to derive one more column which is 1 upon sine theta. So for all the values of theta, so if this is 22 degrees, so this is 22 degrees, so I have to find out what is of 1 upon sine 22 degrees, and this table is what we need to plot, not theta and ft. So this is a very important thing. Ft and 1 upon sine theta is what we need to plot, because x-axis is 1 upon sine theta. So make sure you always check what is given. So we have to just compute all the 1 upon sine theta values. So when you compute the values and you graph a plot, you will get a graph something like this. Okay, now once we have a graph, the question wants us to find out the best fit line that you drew in part C3. Calculate an experimental value for the mass m of the meter stick. Okay, what was the formula we knew? So ft is equals to, what was the formula? 5 mg is 6 one time 1 upon sine theta. So 5 mg upon 6 times 1 upon sine theta. So now if I figure out what is the slope, I already know, I can simply find out the value of m. So the value of slope will be equals to 5 mg upon 6. And how can I find out the slope? I can see that this is one of the values which is 4 and 0.5. So I can say this value is 0.5 comma 4, and I can say there is one more exact value, I can find it over here, that is 2.4 comma it is 20. So using this 2.4 comma 20, so I have 2.4 comma 20, and I have one more 0.5 comma, what was the other, it was 4. So 0.5 comma 4. Now what is slope? Slope is simply y2 minus y1 upon x2 minus x1. So y2 minus y1 is 20 minus 4, 20 minus 4, and 2.4 minus 0.5. So 2.4 minus 0.5. So once you figure out the slope, is what you will get is 8.4 newtons. Okay, so now if I put all the values over here, this is 8.4 is equals to 5 mg upon 6. Putting the values, it should be 8.4 multiplied by 6 divided by 5 multiplied by the value of g is going to be 9.8 is equals to m. So you should be getting the value of m as 1 kg. Okay, approximately you will get the value of 1 kg. Okay, perfect. Okay, welcome to the series where we will be discussing previous year questions of AB Physics 1. In this video, we will be discussing question number 4 of year 2025. Okay, so there are two scenarios given. A swimmer holds a block of mass m at rest in a tank of a fresh water with the density ρ1, as shown in figure. The block is released from rest and accelerates upward with an initial acceleration which is given as a1. All friction forces are negligible, so no friction. And in scenario 2, the swimmer holds the same block at rest in a tank of salt water with density ρ2, where ρ2 is greater than ρ1. The swimmer again releases the block from rest and the block accelerates upward with now an initial acceleration of a2. There here it was a1, here it is a2. All friction forces are again negligible. Okay, let's understand the system what we have right now. So in the first scenario, if this is a fresh water case, let's say this is the free body diagram of a mass m. So I can say that the downward force which is pulling it downward is going to be the gravity, that is going to be mg, and the upward force is definitely going to be the buoyant force fb. Let's consider fb, and here this is the case of, let's say, density ρ1. Similar case I can also draw for this one which is the density ρ2. So I'll have same thing, and this is, I can say that buoyant force is going to be ρ1 times the volume times the gravity g. Now this is the density of ρ2, this is where I have the mass mg, and the buoyant force fb is going to be rho 2 times Vg. Okay. Now what is acceleration? Acceleration is nothing but net force is equals to mnet is equals to mass times acceleration. So the more the net force, the more is going to be the acceleration. So net force here I can say it is rho 1 Vg minus mg equals to ma. And here I can say that I can write it as a1 and I can write it here as a1. And in this case I will have the buoyant force Fb, which is rho 2 Vg minus mg is going to be same, m is going to be same, and here I will have is a2. Now given to us there is a condition which is rho 2 is greater than rho 1. This is the condition given. So as rho 2 is, as the value of rho 2 is greater than rho 1, can I say that the buoyant force of rho 2 will also be greater, because Vg is constant. If I multiply by a positive value Vg, so rho 2 Vg is also going to be greater than rho 1 Vg. Now if I subtract mg on both the sides, so rho 2 Vg minus mg is greater than rho 1 Vg minus mg, and this is what we have as ma2 greater than ma1. So I can say that the acceleration 2 is greater than acceleration 1. Okay, so this is what we can understand from these two scenarios. Let's go to the question. What does it say? Indicate whether a1 is greater than, less than, or equal to a2 by writing one of the following. So yeah, definitely a1 is less than a2. Justify your answer in terms of all forces exerted on the block in each scenario. Use qualitative reasoning beyond referencing equations. So I can say that we do not need to reference equation. We can only say that the force, the buoyant force, is directly proportional to the density, and as the downward force, which is the gravity force, is constant in both the cases, it only depends on the upward force. So more the buoyant force, if the more buoyant force, the acceleration is going to be more. Hence buoyant force is dependent on density. So as rho 2 is greater than rho 1, it simply tells us that the buoyant force of 2 is going to be greater than buoyant force of 1. That tells us that the acceleration of 2 is going to be greater than acceleration of 1. Okay, so this is what we can write over here. Next, consider the general case where a block of mass m and a volume v, so mass is m, volume is v, is completely submerged in a fluid of density rho. Starting with Newton's second law, derive an expression for the initial upward acceleration a of the block when the block is released from rest. So what we just did, so here I will have the mass mg, and on the top I will have a buoyant force. Here in this case it is rho vg, the volume is v, the density is rho. Now we know that F net should be equals to mass times acceleration. So F net we have is rho vg minus mg's downward force is equals to ma. If I divide on both the sides by mass, I will get is rho vg upon m minus gravity is equals to acceleration a. So this is the expression for initial upward acceleration a. Okay, very good. Now last thing, indicate whether the expression for the acceleration a you derived in part b is or is not consistent with the claim made in part a. So here also I can say that acceleration, the value of g is a constant value. This is a constant value. M is constant, v is constant, g is also constant. So again I can say that acceleration is directly proportional to the density rho. So if the density is more, definitely the acceleration is going to be more. So I can say that the explanation is definitely consistent. Whatever we gave the explanation is part A is already consistent. Now justify your answer by your derivation in part B. So from that derivation I can say that as acceleration is equals to rho vg upon m minus g, so as acceleration is directly proportional to rho, so if rho 2 is greater than rho 1, hence acceleration 2 should be also greater than acceleration 1. So this should be our final answer. Okay, we have discussed all the questions of free response question of 2025. If you have any doubts, put your doubts in the comment section. I will help you over there.